So I'm going to really quickly review intermolecular forces with you, which you looked at over the summer. Remember, intermolecular forces are the attractive forces between two different molecules, okay? And so we have three different types of intermolecular forces: hydrogen bonding, dipole-dipole forces, and London dispersion forces. So let's talk about hydrogen bonding first. So in hydrogen bonding, remember, to have hydrogen bonding, your molecule must be polar, and that's key. So NH4 plus ammonium, which is nonpolar, would not have hydrogen bonding. And you must have hydrogen. Remember that hydrogen has to be bound to fluorine, oxygen, or nitrogen. So if you have a hydrogen that's bound to carbon, for example, it won't work. And you have to have fluorine, oxygen, or nitrogen. So the hydrogen of one molecule, which must be bound to fluorine, oxygen, or nitrogen, would then be attracted to the fluorine, oxygen, or nitrogen of a different molecule, okay? Now, in general, when we're comparing the strengths of intermolecular forces, in general, hydrogen bonding tends to be the strongest. Now, that is the case unless you have a huge molecule that has so many electrons that its London dispersion forces are stronger than hydrogen bonding or dipole-dipole forces of another molecule. And the reason why you need a large molecule with a lot of electrons, remember, the more electrons you have, the more polarizable that molecule is. So if a molecule is so large and so polarizable that its London dispersion forces end up being stronger than hydrogen bonding or dipole-dipole forces, that's a case where hydrogen bonding would not be your strongest intermolecular attraction. Okay, now, well, what happens if both of the molecules you're comparing have hydrogen bonding? Well, in that case, then you look at the molecules and decide, okay, which one can form more hydrogen bonds? So for example, if I gave you these two molecules here, notice that the first molecule has an OH in the beginning and an OH at the end, while the first one only has an OH at the beginning, which means that the first molecule can form more hydrogen bonds than the second, and therefore its intermolecular attractions would be stronger. And remember, our way of measuring the strength of intermolecular attractions is by looking at boiling point or melting point. The higher your boiling point or the higher your melting point, the temperature at which it boils or it melts, the stronger your intermolecular attractions are going to be. All right, so that's everything for hydrogen bonding. What about dipole-dipole forces? Well, to have dipole-dipole forces, you must have a molecule that is polar. Okay, so hydrogen bonding is a type of dipole-dipole force. So for example, for that the two molecules that I showed that example for, if I said, hey, what are the types of intermolecular attractions that these experience, you would say hydrogen bonding, dipole-dipole, and London dispersion forces. Now, you don't have to say dipole-dipole forces because hydrogen bonding is a type of dipole-dipole force, but you can always say all three of them, okay? And so if you notice, I included London dispersion forces because London dispersion forces exist in all atoms and molecules, because all atoms and molecules, other than the hydrogen ion, have electrons, and therefore since they're always moving, there's that potential to form a temporary dipole, and that temporary dipole, which results in attractive forces, that is your London dispersion force. So remember, in terms of comparing the strength of London dispersion forces, if you have two molecules that only have London dispersion forces, remember the one that has more electrons is going to be more polarizable, and therefore it is going to have the stronger London dispersion force.
So since we've talked about intermolecular forces, we need to really quickly talk about the process of dissolving in water. Now, we're going to get into this in much more detail in Big Idea 5, but I first wanted to address it here because we've now talked about intermolecular forces. So if you see a compound like this, CH3CH2OH, you immediately know that it's going to have hydrogen bonding because it's got a hydrogen that is chemically bound to an oxygen. So if I were to draw this, it would look like this, okay? And so the main point for you to know is that it can form a hydrogen bond with itself because if you had another molecule, okay, it would look like this, okay? And so it can form hydrogen bonding with itself because the oxygen from one molecule will form a hydrogen bond with the hydrogen of the other molecule. So it'll look like that. So that's hydrogen bonding. And so this molecule here is going to have a higher boiling point than something that doesn't have hydrogen bonding, But what about dissolving in water? Okay, what causes this molecule, ethanol, to be able to dissolve so well in water? In previous science classes, you might have said, oh, well, since ethanol is polar and water is polar, like dissolves like, and left it at that. Well, that's not a good enough explanation in this class. And so instead, what we have to do is we have to talk about the intermolecular attractions between molecules, the intermolecular attractions between ethanol and water. So let's actually draw that out. So here's my ethanol molecule, and it can actually form, since we've got water here, it can and will form hydrogen bonds with water. So this is one possible hydrogen bond here. If you have another water molecule, then the oxygen from the water could form a hydrogen bond with ethanol here. So those are all possible hydrogen bonds. So when explaining why ethanol is good at dissolving in water, you need to discuss the fact that it can form hydrogen bonds in water. Okay, not too bad. Let's look at the next example. Okay, when I draw this molecule out, this is dimethyl ether. So looking at this molecule, it is polar, but notice it does not have any hydrogens bound to its oxygen. So if I were to have another dimethyl ether molecule right next to it, because these guys have a permanent dipole, they will form dipole-dipole attractions with each other. They cannot form hydrogen bonds. Okay, so if I were to draw the attractive force, that would be dipole-dipole forces. Okay, well, dimethyl ether is actually pretty good at dissolving in water. Why? Well, you might want to immediately and blindly say, well, that's because it can form dipole-dipole forces with water. But is that the strongest force it can form with water? Let's look. So here's my dimethyl ether. Notice the reason why it didn't have hydrogen bonding with itself was because its hydrogens were not bound to carbon. Well, what if water comes along? So remember, to have hydrogen bonding, you need fluorine, oxygen, or nitrogen in one molecule, and then you need a hydrogen in a different molecule that is chemically bound to either fluorine, oxygen, or nitrogen. Well, I have the hydrogen that is chemically bound to oxygen contributed by water. That's my hydrogen. And I have an oxygen in a different molecule. So what that tells me is actually it can form hydrogen bonds. Okay, so while dimethyl ether by itself can only form dipole-dipole forces because it's polar and its hydrogens are not chemically bound to oxygen, fluorine, or nitrogen, when I'm dissolving it in water, it can actually form hydrogen bonds. So do be careful, because if you have a polar molecule that has fluorine, oxygen, or nitrogen, although it normally wouldn't be able to form hydrogen bonds with itself, when you dissolve it in water, because water contributes the necessary hydrogen for hydrogen bonding, it will actually form hydrogen bonds with water and therefore be able to dissolve well. Okay, what about CH4? Well, CH4, we know, is nonpolar. And since it's nonpolar, the only type of attractive force it can form with itself is London dispersion forces. Okay? Well, what force can it form with? What attractive force can it form with water? Well, we've got oxygen, we've got water here. Okay. What is the attractive force? Well, would this be considered a hydrogen bond? And the answer is no, it wouldn't, because this molecule, methane, is not polar, and the hydrogen is not bound to fluorine, oxygen, or nitrogen. So the only attractive force it can form with water is London dispersion forces. So that's why methane is not soluble in water. It's not because methane's nonpolar and like dissolves like, it's because the strongest force it can form with water is London dispersion forces. And there are a number of other forces that have to be broken in order for that attractive force to form. So if the attractive force is very weak, like just London dispersion forces, then the molecule will not dissolve in water. However, if it can form a strong force like hydrogen bonding, then it will dissolve in water. And so that's why ethanol and dimethyl ether do dissolve in water.
Now that we've gone over intermolecular attractions and talked about what exactly happens when we are dissolving a solute in a solvent with respect to the intermolecular attractions, I needed to talk about one last thing, and that is what exactly happens if we break intermolecular attractions. So when we break intermolecular attractions or intermolecular forces, what happens is that we actually just change the state of matter of a substance. So for example, if we have a solid and we break the intermolecular attractions there, you'd become a liquid. If you had a liquid and you broke intermolecular attractions, it would become a gas. And something that we looked at in first year chemistry is this heating curve right here. So just as a review, remember if you start at the very base of this, heating curve, what's going to happen is you move from left to right, you are going to be putting heat into that substance, whatever it might be. So the first thing that happens is that if you start with a solid, if you put heat into it, the temperature of that solid is going to increase. And the important point is the next step. So notice when you go from a solid to a liquid, where it shows melting, notice that it levels off. And it levels off because the temperature does not change when you have a change of state of matter. And same thing with boiling, as you can see at the top of the graph. Okay, so for melting and boiling, or condensing and freezing, you don't have a change in temperature. And so the question is, well, what happens to that energy, right? When you're going from left to right, you're putting heat into the system. Where does it go if it's not being used to change the temperature? And the answer is it's being used to break intermolecular attractions. Okay. In reverse, if you're going from right to left, so let's say you're going from a gas to a liquid, if you are condensing or if you are freezing, that energy is being released when you are forming intermolecular attractions. Okay, so going from left to right, for melting and for boiling, energy is put in to break intermolecular attractions, and going from right to left, energy is released in order to form intermolecular attractions. Now, if we are breaking or forming intermolecular attractions, remember, those are attractions between two different molecules. And so you are simply going to be changing the state of matter, so this is going to be a physical change. Okay? The last thing I wanted to quickly mention, notice for melting versus boiling, notice that the length of that line for melting is much shorter than the length for boiling. And the reason why, and we'll look at this when we get to Big Idea 5 next semester, but boiling requires much more energy, and that's because we have to break way more intermolecular attractions going from a liquid to a gas than from going from a solid to a liquid. So since boiling requires more breakage of intermolecular attractions, the energy required to actually boil is going to be a lot larger, and we see that with that it's almost 4 times the size of the melting line. Okay? Well, what about, and I'm about to bring up intramolecular forces. So remember, intermolecular forces were London dispersion forces, dipole-dipole, and hydrogen bonding. Intramolecular forces, which I'm about to review, are going to be our ionic and our covalent. Okay? Well, for ionic, if I'm breaking ionic bonds, it's a little bit weird because it isn't actually a molecule that we're breaking. So when we break an ionic bond, you're actually just going to be having a physical change. So if you're breaking ionic bonds and no other change occurs, it's going to be a physical change because you're simply changing the state of matter. So you're melting it. Okay? Now, if something else changes, like you're forming new compounds with those ions that have been separated, then yes, that would become a chemical change. Okay? If you have covalent bonds and you're breaking those intramolecular forces, then that would be a chemical change. Okay? So I'm now going to get into, in detail, intramolecular forces. I just wanted to go back and review stuff from first year with respect to what exactly is happening when we're melting and boiling, right? The concept that we are breaking intermolecular attractions, and then also why does temperature not change? Well, it's not changing because I'm either breaking or forming intermolecular attractions, and that's what the energy is used for.
Bonding. Now remember, in an ionic bond, you have metal and a nonmetal with a positive and a negative charge. And so here are some of the characteristics of ionic bonds. The first is that as solids, they do not conduct electricity, and that's key. When they're dissolved in water, however, they do conduct electricity, and that's because when they're dissolved in water, their ions are free to move about and to conduct electricity. They're not held tightly in a solid, and therefore the flow of electrons is much easier because the ions themselves are free from that rigid solid. The next characteristic is when they're solids, because there's a really strong attractive force, they have very, very high melting points. So just as an aside, since I've now talked about ionic bonds, we're going to really quickly discuss factors that affect the strength of ionic bonds. So the first thing for you to know is Coulomb's law. Now, Coulomb's law states that the larger the charge of an ion, so +2 is a larger charge than +1, and the shorter the distance between the nuclei of the ions, the stronger the bond, the ionic bond is. Well, that attraction, that bond energy, when we're talking about ionic bonds, we call that the lattice energy. So the higher the charge and the shorter the distance between the nuclei, the stronger that attraction is, the stronger that lattice energy is. Well, how does that translate into actual ionic bonds and being able to compare the strength of ionic bonds for different ionic compounds? Well, the first thing is the charge. Okay? So the higher the charge of an ion, the larger the charge, the stronger the bond's going to be. So if I were to compare the ionic bond of sodium chloride, NaCl, versus magnesium oxide, MgO, since magnesium and oxygen have a +2 and -2 charge, that tells us that the ionic bond is going to be stronger for magnesium oxide versus sodium chloride, which only has a +1 and a -1 charge. The other factor that affects the strength of ionic bonds is the size of the ion. Okay, so for example, if I were to compare the strength of sodium chloride and lithium fluoride, if you notice, lithium and fluorine ions, they are smaller than sodium and chlorine, which tells you that lithium fluoride is going to have a stronger ionic bond. It's going to have a higher lattice energy because they are smaller ions. Now the question becomes, well, what if they have a different charge and a different size? Well, charge is the ultimate decider in it. So if they have different charges, if two ionic compounds have different charges, charge is the most important thing. So if I were to compare lithium chloride, for example, and magnesium oxide, since magnesium and oxygen have a +2 and -2 charge, that takes precedence. The size of the ions does not matter. However, if your ions in your ionic bond have the same charge, then you go and compare the size of the ions. So those are questions that you'll see a lot, and you can also see in the real world when you're comparing the strength of ionic bonds, specifically when we're looking at melting points and boiling points, even though we're really not going to see an ionic bond, an ionic compound melting or boiling, but if we would be able to determine which would have a higher melting point or a higher boiling point just by comparing the charge and the size. Specifically, the stronger the ionic bond, the higher the melting point or the boiling point would be. Metallic bonds exist when you have metals. So here you have gold, and the way that we describe metallic bonds is that we say it is an electron sea, meaning that you have a bunch of gold atoms, and instead of sharing or donating their electrons move freely through all of the different metals. And so it's a sea model. Now let's look at some of the characteristics of metallic bonds. The first is that they have a high melting point, not as high as ionic bonds, but still a high melting point. It takes a good amount of heat to melt a liquid. And they are great conductors of electricity when they're solids. And so that's how they're different from ionic bonds as well, because they're great at conducting electricity even when they are solids. Covalent bonds, there are going to be two different types that we look at. The first that we look at are just molecular solids. Molecular solids are discrete molecules like carbon dioxide or any of the other molecular compounds that we've looked at. And so when we're describing characteristics of molecular solids, what we use to describe them and to dictate what they're going to act like,
we look at their intermolecular forces, which includes hydrogen bonding, dipole-dipole, or London dispersion forces.
Remember, hydrogen bonding would have the highest melting and boiling points, while London dispersion forces would have the lowest melting and boiling points, simply because London dispersion forces are the weakest type of intermolecular force. So those are molecular solids.
The last characteristic
is that they cannot conduct electricity, period. No matter, even if you try and dissolve them in water, which unless they are polar, you aren't able to, but they do not conduct electricity. The other type of covalent bond, the other form it can take is in the form of covalent network solids. Now, covalent network solids might sound new and unusual, but you've actually had a lot of experience with them. They have an extremely high melting point, and they have an extremely high melting point because, as you can see, for example, for diamond, a covalent network solid consists of atoms that are all tied together by covalent bonds. It's not a molecular solid in which there are covalent bonds, but then they rely on intermolecular forces. All of the attractions in a covalent network solid are the intramolecular force of covalent bonding. And so as a result, they have a very, very, very high melting point. And two examples that you see on a daily basis are diamond and graphite. Now, really just as a quick aside, graphite it looks way different than diamond. It's an allotrope of diamond, meaning that the bonding is just slightly different. And the reason why is graphite, covalent bonding exists in layers between those carbon atoms, but then there are actually gaps. And as a result, graphite forms sheets, as opposed to diamond, where all of the carbon atoms are attracted to one another. So that's why graphite's so easy to use to write, because those atoms will simply move past one another very easily, but still extremely high melting point.
So now that we've talked about the intramolecular attractions, ionic bonding, metallic bonding, and covalent bonding, whether we have a molecular solid or a covalent network solid, and I've talked about the melting points, etc., let's actually compare their melting points. And then this would also correlate with their boiling points as well, right? And ultimately, melting point and boiling point is simply telling you which is the strongest, right? So the strongest intramolecular attraction is going to be your covalent network solid. And that's because every single electron is going to be in a covalent bond. So all of the atoms are going to be connected via covalent bonds, okay? Obviously, that does not apply for graphite, but I'll talk about graphite a little bit later on. But covalent network solids would be the strongest, followed by ionic compounds. So that's why you've never seen sodium chloride or any sort of ionic compound melted before. Followed by metallic solids, so not too hard to melt, but still requires a good amount of heat. Followed by molecular solids. Now remember, molecular solids are going to be broken up into whether or not they're polar or nonpolar. So remember, here now, because we're talking about molecular solids, we're going to be talking about intermolecular attractions when we're talking about their melting or their boiling point. So for a molecular solid, remember, if it's polar, it's either going to have dipole-dipole forces or hydrogen bonding. So that is going to have a higher melting point or boiling point than a nonpolar molecule, which would only have London dispersion forces in general. Obviously, there's some exceptions. Okay. Now let's talk about conductivity. So who conducts electricity and why? So first, ionic compounds. Now, compounds that have ionic bonding, when they are solids, their ions are not free to move around, and therefore they do not conduct electricity as solids. However, when they are dissolved in water, or they're dissolved in whatever solvent you want to use, their ions are then free to move around, and therefore they're able to conduct electricity. Okay? So if you ever want to test a compound to see if it's ionic, test its conductivity as a solid. If it doesn't conduct electricity, but when you dissolve it in water, it does, it's going to be ionic bonding. So keeping in mind the fact it's the ions that are free. A lot of people confuse it and say, oh, the electrons are free to move. No, the reason why ionic compounds will conduct electricity in solution is because their ions are free to move around. Okay? Let's talk about metals. Okay? For metallic bonding, they will always conduct electricity in the solid state, and that's because they have a sea of free electrons that are constantly moving around, and therefore they're able to conduct electricity. All right, what about covalent, right? So specifically here, I'm going to be talking about covalent network solids, which you can see in the diagram, but in general, what about molecular solids, right? Do molecular solids conduct electricity? And as I noted before, no, they don't. And the reason why they don't is because their electrons are stuck in covalent bonds, okay? So they don't. Their electrons are stuck in covalent bonds, but there is one exception, and that exception is graphite. Remember, for graphite, as I just stated, they form sheets. right? So all of the carbon atoms are not, every single carbon atom does not have 4 covalent bonds coming off of it. Instead, you will have carbon atoms that have lone pairs of electrons, and that's what enables them to form these sheets that we see in graphite. Well, since those electrons are not stuck in covalent bonds, that means that they are free so that that molecule can actually conduct electricity. So since it has unbound electrons, it is able, graphite specifically is able to conduct electricity. The rest of the molecules that we've looked at, from molecular solids and network covalent, so diamond, silicon dioxide, those are not able to conduct electricity.